Hello and welcome to another video presentation, courtesy of the University of North Texas Physics Department, with the assistance of the Physics Demo Room. My name is Corey Nook, and I'll be assisting today's demonstration, which has to deal with the conservation of angular momentum. Now, this is a rotational analog to the conservation of linear momentum, which hopefully we've discussed already, is that it's the mass times the velocity of an object initially has to equal the mass times its velocity of the object finally in any situation, whether it's a collision or just of an object's velocity or collision occurring. So now remember that the moment of inertia is kind of like the rotational analog to a mass or the linear moment, linear inertia. It's resistance to want to rotate. So with this, we would say, well, with linear momentum, it was the mass times the velocity has to equal the mass times the velocity final. So how do we do this with rotation? Well, with this, we have to kind of look at its mass component or its mass analog, which would be the moment of inertia, as you see on the board, that the initial moment of inertia times the angular frequency or the angular velocity initial has to equal the final moment of inertia times the final angular frequency or angular velocity. So if I was just rotating and I didn't do anything, is that if I was to look at my rotation now and my rotation finally when I make one full turn, when I have my initial velocity already set, it didn't seem like I was changing my speed or my rotations as much. But now it's to say, well, what if all of a sudden I was rotating, and let's say someone else was in the room and passed me a basketball. I now increase the mass that I have. And remember that the moment of inertia usually has to do with the mass and a radius squared term with some other coefficient. So that would also automatically increase my mass. So if the moment of inertia was smaller than the moment of inertial final, my angular velocity has to decrease because my final moment of inertia increased. Well, a lot of times we see this concept every single time the Winter Olympics comes on and we watch figure skating, because most of you are used to seeing a figure skater will have a spinning motion. They'll have their arms out, they are spinning slow, and they bring their arms in and they start spinning faster. That's because the shift in where their mass is, you're now making the radius smaller. You're now changing the moment of inertia. You're making the inertia smaller, so the angular frequency has to increase, so therefore you'll spin faster. We can do a demonstration about this using this rotating platform and some dumbbells. So what I'm going to do is I'm just going to initially just have me spinning. Look, I almost stopped. I brought it in. Almost stopped. And I'm going in. So now I'm going to spin a little bit faster. And I'm going to do it the other way. So I'm going to try to get some good speed at first. Now I'm going to bring them in as I almost fall off the chair. See how with the change of where the mass was distributed, to make it more central and decrease the radius, I increased my moment of inertia, or I decreased my moment of inertia because R got smaller, but the total mass of the system stayed the same. So now that that moment of inertia got smaller, the angular frequency or the angular velocity got bigger. Well, thank you for listening to this video presentation, and have a wonderful day.